Momentum worksheet number 1. Question number 1. We have identical velocities. Object A is 3 times the mass of object B. So because my momentum is equal to m times v, if velocity stays the same and the mass is 3 times greater, then I'm going to have 3 times the momentum. Using the same example here, if I have identical masses and I increase my velocity by 2, increasing my velocity by 2, keeping the mass the same, I'll end up with 2 times the momentum by increasing my velocity by 2. Question number 3. I'm given a net force. I'm given a mass. This mass is in grams, so I immediately want to change that into kilograms for a time period. So I have a net force given, I have a time given, and I have a mass given. The magnitude and the change in momentum. My change in momentum could be mass times change in velocity. However, I'm not given a change in velocity, so I'm going to have to use impulse instead. So for my impulse is my net force multiplied by the time interval. So I end up with a net force of 132 newtons, and I multiply that by a time given to me as 4.5 times 10 to the negative second power, and I end up with an impulse which is equivalent to my change in momentum, which is going to be equal to, so the change in momentum ends up being 5.94 kilogram meters per second. If the initial speed is 0, calculate the speed of the ball as it leaves the pitcher's hand. Well, my change in velocity will be my final velocity minus my initial, which I've already found is 0. So if I can find my change will be my final. And so I'm going to go up here and take my impulse equals change in momentum equation. This is going to be mass times change in velocity. I just found what my impulse is. So my 5.94 impulse is going to be equal to my mass, 0.14, times my change in velocity, again using this original equation here. So when I calculate my change in velocity, because I start at rest, it's going to be my final velocity, and that's going to give me a value of 42.4 meters per second. So that's the speed of the baseball as it leaves the pitcher's hand. Moving on to question number 4, previous problem. So in the previous problem I have my velocity coming in. We're going to apply a force with the bat in the opposite direction. So it says show a diagram. The reason this question exists is so that you realize that the ball coming in and then the ball going out, I have 2 separate directions. Since momentum is a vector, I need to make sure that I account for this by calling one of these a positive and one of these a negative. If I'd like, my picture shows this going to the left, so my velocity or the speed that I found in question number 3, I'm going to say that it's a negative velocity when it comes in, and therefore I get a positive final velocity on my way out. So calculating a change in momentum, the force is going to be pushing in this direction. So my change in momentum is going to be equivalent to my impulse, and impulse is net force times time. So if I take my force of 1320 newtons and I multiply that by 9 times 10 to the negative third seconds, in doing that I will find what my change in momentum is. I get 11.88 kilogram meters per second. That's going to be the change in momentum. Because of the direction I chose, that is going to be a positive, it is a vector. to calculate the final velocity of the ball, I'm going to use my standard change equation. So to figure out this, I need to figure out what my change in momentum is. I'm sorry, my change in velocity. I need to use my change in momentum here. My change in momentum is mass times change in velocity. So 11.88 from above. Mass as given originally was 0.14 times my change of velocity. My change of velocity is calculated to be, what do we have there? About 84 meters per second. I come over here, my change was 84. I'm trying to find my final, and my original was actually going in the negative direction, so minus negative 42.4. The negatives cancel out, and I'm left with 84 minus 42. If I use more exact numbers, I find that my final velocity will be a positive. The opposite direction that I had up here will be a positive 42.5 roughly. So the ball coincidentally ends up leaving the baseball bat at roughly the same speed that it came in. What force is exerted on the bat by the ball supports your answer. This right here is a conceptual question. This question here, if the bat applies a force of 1320 to the ball, then the ball applies the same exact force to the bat. So this right here is going to be 1,320 newtons. Support my answer, Newton's third law. Question number 5. If a car has a mass and a velocity, a second car have the same momentum, this is a pretty straightforward question using m times v. So if I take my mass of 725 and I multiply that by 35 meters per second, that, to make that equal to my mass of 2100 times v, multiply this together, I get about 25,000, but they're not asking for that, it's just asking for a velocity. So 25,000 divided by 2100, we end up with the velocity about 12.1 meters per second. Looking at the back of the same worksheet number 1, question number 6. Draw a force diagram. So I have a rocket. This rocket is going to have a downward force of gravity and an upward applied force that I'm going to call F. So calculate the net force on the rocket. This upward force is given to us as 8.9 times 10 to the 5th. 8.9 times 10 to the 5th. My downward force is given to me as the weight, 43600. And so to determine what my net force will be, I will have an upward 8.9 times 10 to the 5th minus my downward force of gravity, 43,600, and I get a net force that is equal to 846,400 newtons. So that's going to be my net force. I can use that with F equals m times a now, or I can use it with my impulse equation, which is what I'm going to do. I'm going to assume that I'm going to need to use a mass with my momentum question. So what I'm going to do is I'm going to calculate what that mass is by taking my force of gravity, 43600 equals m times 10. So rather easy equation there. My mass will be 4,360 kilograms to be used later. Calculate the time required to reach this velocity. So we're going from 0 to 860 meters per second. So if that's the case, I am going to use my impulse equals my change in momentum. My impulse is going to be my net force times time. equals m times delta v. I'm going from 0 to 860, so I can just use 860 right there. So I have a force already calculated in part A times the time, mass, which I decided to figure out ahead of time, times my change of velocity of 860 meters per second. When I calculate my time, I end up with 4.43 seconds. That will be the time for my rocket to reach the speed of 860 meters per second. If I did net force equals mass times acceleration and use some distance equations, I'd come up with the exact same answer. Question number 7 involves a car traveling at 25 being brought to a stop. If I come to a stop, that means my final velocity is going to be 0. So since our final velocity is 0 in each case, calculate the change in momentum. My change in momentum will equal m times delta v. Let's rewrite that there. M times delta v. Since I'm going from 25 down to 0, my change in velocity will be 0 minus 25 for negative 25. So to figure out my change, mass of the car is given as 2,200. My change in velocity is negative 25. And so for question number 7, I get a change in momentum of negative 55,000 kilogram meter per second. That negative is just the direction I chose as a negative. I decided forward was positive, so going from a positive 25 to 0 is technically a negative. Calculate the net force required to stop the car in each situation. I've got 21 seconds or I've got a quarter second. So if this happens in the 2 different times, my impulse, which is my change in momentum, impulse is net force times time. I'm given a time. I now know what my impulse is already, so if I take my impulse of 55,000 and divide it by each time, I'll figure out the force required, how hard I have to push to make this happen. So negative 55,000 equals my unknown force times my first time of 21 seconds. I get a net force of about 2,619 newtons. If I do the same work for my second time given, the time is much, much smaller, 0.25. So 55,000 divided by 0.25, the same as multiplying it by 4, I get 220,000 newtons. We can see the enormous difference in the amount of force. This would be gradually applying the brakes. This would be smashing into a wall. So similar to our safety discussion involving helmets, I can see that an enormous difference in the force by changing the time. So if I increase the time, we had 21 seconds. Increasing the time means less force, which would be safer for my driver. Question number 8. Use any method to calculate the landing velocity of the ball. Given the choice, I'm going to say that I go from all potential energy to all kinetic energy. I think that will be a very convenient way to do this question. If we remember all the way back to September, we know that mass doesn't matter for our falling object if we ignore air resistance. And so I'm left with g of 10, height of 1, 1/2 v squared. Our velocity when this golf ball hits the ground is going to be 4.47 meters per second. It is going to be moving down. One thing energy doesn't do for us is give us a direction, so I am going to decide to put that direction in myself, negative 4.47, because it's falling downward. So calculate the instantaneous momentum of the ball as it reaches the floor. It's a fancy way of saying what's the momentum. So there's my equation. The mass, I have a weight given to me, so off to the side I'm going to have to calculate what that mass is by taking 0.45 equals mass times 10. So some simple math there to get my mass of 0.045. So 0.045 for a mass multiplied by my downward velocity and the momentum of my ball the moment it strikes the floor is going to be negative 0.201 kilogram meter per second. So that will be the momentum as I strike the ground. Show a diagram and calculate the change in momentum during the contact with the floor. We're told that the ball leaves the floor with an equal and opposite velocity. So that means I'll have an upward velocity of 4.47. So if I do my change in momentum, that's going to be my final minus my initial. So my change, my final is going to be upward 0.201, doing the same math here but with a positive, minus the original, which was a negative 0.201, minus a negative gives me a positive, and I end up with 0.402 kilogram meter per second. That will be the change in momentum that we experience. And the last, if the golf ball is in contact with the floor for a given amount of time, we've done this a number of times already now, my impulse is going to be my change in momentum, and my impulse is calculated by doing force times time. My change in momentum is right there, 0.04, so I get 0.402 equals the unknown force on the golf ball times 4 times 10 to the negative 4. I do my work, and the final answer for this worksheet is going to be a net force of right around 1,006 newtons. The number seems rather high, but keep in mind we have a very big velocity change in a very, very small amount of time. The golf ball has to be pushed very hard to make that happen.